Welcome back. Today's recording is going to deal with nuclear decay equations. And so this will require a little bit of note-taking for sure. So if you remember, when we write a regular chemical equation, reactants are on the left and products are on the right. Example that we've already looked at is when hydrogen and oxygen gas combine to form water molecules. Remember, we have to conserve matter, so we have to have the same number of atoms of hydrogen on both sides, so we add in our coefficients. We don't have to do quite as much of that with nuclear decay equations, but sometimes you will need to add in coefficients. So just a little reminder. In a nuclear decay equation, you start with some sort of particles, radioactive particles, and you end with some number of particles on the product side. But instead of calling it reactants and products, we start with what we call the parent nuclide on the left and end with daughter nuclides on the right. A couple other terms that we need to be familiar with. Decay. And of course, decay is a word you've probably heard before. Decay means something falls apart. When we're talking about a nuclear decay, the parent nuclide will fall apart. And with the particle that's mentioned, like alpha decay or beta decay, that particle is on the product side or the daughter nuclide side of the equation. So we'll see a lot of that. Another thing that can happen is capture. So a particle can be captured by the parent nuclide. So the particle, like positron or beta capture or whatever, the parent nuclide captures has this particle stick to it, and then usually it breaks into other pieces as well. So with with decay equations, the particle that they say is going to be on the right-hand side of the equation. With the capture equation, the particle that's mentioned is going to be on the left-hand side, on the reactant or parent nuclide side. One other thing to mention and remind you of is when we write particles and when we write these equations, we put the mass number first. That's also the isotope number. And we put the proton number or atomic number at the bottom, and then whatever symbol we have for our element. So we're going to be focusing on elements that are at the bottom of the periodic table as well, because those are everything after lead, after number 82. All of those elements only have radioactive nuclei. So again, the mass number is protons added to neutrons. The atomic number is just the protons, and of course, if you subtract the small number from the big number, you'll get how many neutrons. Sometimes neutrons are ejected or captured in equations. So some particle symbolization that you need to know. This is similar to the table that was on your note sheet. Alpha radiation, remember alpha is the first letter of the Greek alphabet, looks like an A. An alpha particle has an atomic mass value of 4, has +2 charge, and that's because it has 2 protons, and then 4 minus 2, it has 2 neutrons. Beta particles, Greek letter B, is a very, very small mass. That's because it's an electron. It has a -1 charge, and it's a high-speed electron coming out of the nucleus. Finally, gamma rays are just energy beams, if you will. They don't have a charge and they don't have mass, and we'll just use that bottom loopy part of a cursive G to represent gamma. Some books use all these different formats for alpha particles. I prefer to use 42He because it's a helium nucleus. I prefer to use 0, -1E, the E to tell me it's an electron, the -1, because not just because of the charge, it's because of how it changes the nucleus. We'll get into that in a minute. And then gamma, we just use the gamma. It doesn't change the contents of the nucleus, it just makes it less energetic when gamma rays are emitted. Next particle that you need to know is the neutron, and we put a 1 on top. Remember, 1's the mass number, neutrons plus protons. A neutron does not have any protons, so 0 for atomic number and then little n for neutron. A proton, because almost all of hydrogen atoms are just a proton with an electron if they're neutral. 1 for the atomic number, 1 plus 0, protons plus neutrons, is 1 for the mass number. And then we use the symbol H for hydrogen. And then finally, positron, which is the antimatter component, equal and opposite to a beta particle. So we call it a positron. It's a positive charge. It's the size of an electron. No neutrons, no protons in it. One weird thing that can happen sometimes, and we'll talk more about going the other way as well, but sometimes when a photon, an energy beam, if you will, strikes a nucleus, an electron and a positron are emitted. These are real. Positrons are real, and they're called antimatter. When an electron, a beta particle, and a positron strike each other, they annihilate each other and become energy. So this can go both ways, but we're just focusing right now on positron. All right, the first type of radiation is alpha radiation. And again, that means that an alpha particle gets emitted. Okay, it comes out of the nucleus. If we start with uranium-238 and an alpha particle comes out, there's going to be less stuff in the nucleus. Okay, 2 less protons, 4 minus 2, 2 less neutrons. And so when that happens, I like to think of these as like two really simple math problems. In the top, you've got 238, and we don't usually say equals 2, but we will for this situation. 234 plus 4. Okay? And uranium is element 92, so when 2 protons come out of it, we end up with 90. And element 90, the element whose atoms have 90 protons, is thorium. Beta radiation is a little different. Again, how in the heck does an electron come out of the nucleus? Well, it's weird. So all this gobbledygook over here you don't need to know, but you do need to know that neutrons are made of quarks, 1 up and 2 down quarks, and a neutron can turn into a proton, and that makes 2 ups and 1 down quark. They're very slightly different in mass right here, and they have the same, mass is here, 1.6749, 1.6726 times 10 to the minus 27. They have neutrons are neutral and protons are positive, but when this happens, an electron gets emitted from the nucleus. It's weird. All right, beta radiation comes from that electron, a beta particle, coming out of the nucleus. So why does that happen? Because a neutron can turn into a proton. And using that same format, again, looking at the numerator, 1 equals 1 plus 0, no brainer. 0 is equal to 1 minus 1. Okay, so this notation helps you see how that can happen, and of course beta particles can come out of large nuclei, not just from neutrons. So here's carbon-14. What's that saying? Carbon is element 6, 6 protons. 14 means it has 8 neutrons. If a beta particle comes out of a carbon-14 nucleus, you end up getting nitrogen. Nice, stable, good old, normal nitrogen. So again, 14 equals 14 plus 0. So the mass number doesn't change. Okay. And for protons, the atomic number goes from 6 to 7, because 7 plus a minus 1 is 6. So what's happened? You've got 1 more proton. The mass number stays the same, so that means you have 1 less neutron when beta decay happens. And this happens all the time. In all living organisms, we have carbon-14, a very small amount. It decays every about 4,000 years. For now is good enough. And so the amount of carbon-14 that you ingest stops when you die or any organism dies, and we can use this to age date some things. Gamma rays don't change the composition of a nucleus, but sometimes particles come out as well. So if we start with thorium, it's a common gamma emitter. Thorium's element 90. Alpha particle will often also come out. So again, 230 is equal to something plus 4. It's just like a baby algebra problem. 90 is equal to something plus 2. And so 230 minus 4, of course, is 226. 90 minus 2 is 88, and that element is radium. And remember, we put after the element's name, we put the isotope mass number value because there's different forms. And you're going to have a periodic table to be able to solve these problems and figure out what the other element is. Okay? This is a good quick overview of nuclear equations, as is this one. And I'll have you watch both of them just as a review. Alpha particles are the least penetrating particles. They're easy to block. They're the least damaging unless you breathe them in. And so gamma rays are the most penetrating. It's almost impossible to completely block them. It takes lots of lead and concrete. It's also so damaging. It's what we call ionizing. It knocks the electrons off of atoms, which prevents them from bonding and causes free radicals in your body, which you may have heard of, which are really bad for you. So this is supposed to represent your skin, some bone, some other tissue in your body. So this is like a muscle, a subcutaneous tissue. Alpha particles will be blocked by your skin. Beta will get into the soft tissue around your bones, and gamma rays just go right on through. This represents the fact that just a little bit of water, 0.03 of a millimeter, will block alpha radiation. Beta rays need a couple millimeters. Gamma radiation needs 10 centimeters, which is about 4 inches. So a lot of nuclear waste is stored underwater to prevent the radiation from escaping. And then this table is a summary of all the information that we've gone over so far. And it is in your textbook at the end of section 1 of chapter 25. So most of the rest of our discussion on radiation will focus on the use of radiation for medicine and for power, and the fact that it is also quite dangerous to store. All right, that ends our discussion for today. Have a wonderful rest of your day. Take good care. See you next time.